This is the lecture for the chapter Semiconductor and Devices, and in this lecture I will discuss about the application of PN junction diode. This is PN junction diode as rectifier. The PN junction diode is very important element and it has huge application in electronics, but today I decided to discuss about rectifier. So first of all I will say what is rectifier. Rectifier is a device that can convert AC signal to a DC signal, and the process of conversion from AC to DC is called rectification. Rectifier are classified into two categories: half wave rectifier, rectifier classified into two categories: half wave rectifier and another one full wave rectifier. Full wave rectifier. But in this class I will discuss half wave rectifiers. Let's see the circuit diagram. This is the circuit diagram of a half wave rectifier, and the circuit consists of a step down transformer. This is the step down transformer, a PN junction diode, and this is load resistance. We all know about transformer. Transformer has two coils. This is primary coil and this is secondary coil, and depending on the number of turns in the primary and secondary, transformer classified into two categories. Let's say the number of turns in the primary is N1 and number of turns in the N2. When N2 greater than N1 means number of turns in the secondary is greater than the primary, then this type of transformer produce high voltage from low AC voltage. So this type of transformer is called step up transformers. Step up transformer for step up transformer, the number of turns in the secondary is greater, and this type of transformer is used at power station. But when the number of turns in the secondary is greater, N1 is greater than N2, then this type of transformer is called step down transformers. And step down transformer produce low voltage from high voltage. And since the PN junction diode is used for rectification and it is semiconductor device and it operates with very small voltage, so here step down transformer is required. Okay. What is the working principle of a transformer? Actually, transformer does not work with DC signal. If we apply DC signal here at the primary terminal of the transformer, for DC signal a constant current flowing in the primary coil, so constant magnetic field develop in that region. So the magnetic flux link with the secondary but does not change since the magnetic field is constant. So we know according to the Lenz law, EMF is equal to minus d phi by dt, but since there is no change in flux in the secondary, so the EMF does not induced at the secondary. But if we apply AC signal means this is the AC signal change the direction with time, so the AC signal means in the primary a variable current flowing, and so a variable magnetic field is developed also, and due to which a flux change at the secondary, so EMF induced according to the relation. Thus the step down transformer transform AC voltage, obviously high to low voltage, so the transformer work with electromagnetic induction, and obviously transformer work with AC signal. Transformer does not control the DC signal. Now I want to explain the operation of rectifiers. Let a AC signal is applied at the primary of the primary terminals of the transformers. And during the positive half cycle, this is the positive half cycle, this is the negative half cycle. During the positive half cycle, upper side of the secondary become positive and lower negative. So during the positive half cycle, P side of the PN junction diode get positive potential and N side get negative potential. So the PN junction diode is forward bias, and we already discussed about biasing of PN junction diode, and we know PN junction diode offer very small resistance when the PN junction diode is forward biased. And in ideal case, PN junction diode offer zero resistance. Thus, in forward bias condition, PN junction diode behave as a short circuit. But in the reverse bias condition, PN junction diode offer very high resistance. So PN junction diode behave as a open circuit. Thus, PN junction diode conduct electricity only in one direction, and this character of the PN junction diode is used for the rectification, and this is the working principle of the rectifier also. Now let's see. So during the positive half cycle, the upper side become positive, lower side is become negative, and so during the positive half cycle, the PN junction diode is forward biased, and PN junction diode behave as a short circuit. So high current passing through the circuit. এখানে আমার ক্যাপাসিটিটা আমি এখন কনসিডার করব না, তাহলে আমার কি হবে, এখানে একটা হাই কারেন্ট ফ্লো হবে ইন দ্য রেকটিফায়ার সার্কিট, অ্যান্ড সো a high voltage appear across the load. Now for the negative half cycle, what happened? During the negative cycle, the upper side become negative and lower side become positive. So the PN junction diode for negative half cycle, P side get negative potential and N side get positive potential. So the PN junction diode is reverse bias, and in reverse bias condition, PN junction diode offer very high resistance and behaves open circuit. So no current flowing in the circuit during the negative cycle. Okay, so no voltage appear across the load resistance. So আউটপুট ওয়েভফর্মটা কি হবে হাফ ওয়েভ রেকটিফায়ার ক্ষেত্রে? লেটস সে দিস ইজ দ্য এসি ইনপুট ওয়েভফর্ম, and since in the half wave rectifier current flowing in the rectifier circuit only during the positive half cycle, so this is the output waveform. This is the only during the positive half cycle we get the output, and all the negative half cycle clipped out, কোনো কারেন্ট ফ্লো হবে না। তাহলে this is the output waveform. Thus the output waveform is unidirectional. সেখানে আমরা নেগেটিভ পিকটা সেখানে ক্লিপ অফ করে দিচ্ছে, নেগেটিভ পিকগুলো কিন্তু আমরা পাচ্ছি না। Thus the output waveform is unidirectional, but output is pulsating in nature, is not constant. That means the output of the rectifier is not pure DC. There is AC also, and the presence of the AC in the rectifier output is called the ripple, and ripple factor is RMS value of the AC component of the load current to the DC is called the ripple factor. So this is the mathematical expression of the ripple factor. AC component, RMS value of the AC component of load current to the average value of the load current. Now I want to calculate the value of a ripple factor, and also I want to calculate the efficiency of rectification. Efficiency of rectification means কতটা আমাদের এসিকে সে ডিসিতে ট্রান্সফর্ম করতে পারছে। সো টু ক্যালকুলেট দ্য রিপল ফ্যাক্টর and efficiency of rectification, first I have to calculate the current in the rectifier circuit. And let's say during the positive half cycle, EMF induced at the input of the rectifier is EM sin omega t. This amount of EMF induced at the secondary. So the current in the circuit, this is the expression EM sin omega t by RL plus RF. RL is the load resistance and RF is the resistance provided by PN junction diode, and this is obviously in the forward bias condition. Obviously, this is very small. So this is the expression of the current, and this is equal to I0 sin omega t. Here I0 is equal to Em by R plus Rf, and this current flowing in the rectifier circuit only during the positive half. So that this is the range of the phase angle, and during the negative half cycle, no current flowing in the rectifier circuit. Okay, so no current flowing in the circuit, and this is the AC current flowing in the circuit. Now I want to calculate the average value of the load current. So this current is also flowing through the load resistance. So the average value of the load current I DC is equal to I0 sin omega t represent the instantaneous value. So the current in the d omega t phase angle, this is the current. So the total current in 0 to 2 pi phase angle, this is the total current. And so here since the current flowing only during the positive half cycle, so 0 to 2 pi I is the instantaneous valence of the current d omega t, and this current in 0 to 2 pi phase angle, so the per unit phase angle, this is 1 by 2 pi, and this is equal to 1 by 2 pi 0 to pi during the positive half cycle. What is the value of the AC current? And this is I0 sin omega t d omega t plus pi to 2 pi 0 d omega t, no current flowing in the positive half cycle, and by integrating we get I0 by pi. So this is the average value of the load current. Now what will be the RMS value of the AC current flowing in the rectifier circuit? And this is IRMS is equal to, RMS mean root mean square. So the total value of the square 0 to 2 pi range is I square d omega t, and average and the root. So this is the root mean square. Square mean the root. Now 1 by 2 pi, since current flowing in the rectifier circuit only during the positive half cycle, so only 0 to pi range current power, and this is equal to I0 square sin square omega t d omega t, and pi to 2 pi range, no current flowing in the circuit. Okay, and by integrating we get I0 by 2. So this is the RMS value of the AC current flowing in the rectifier circuit. Now what will be the value of the RMS current in the load? RMS value of the AC component of the load current in the circuit. AC current flowing is I0 sin omega t. I current flowing in the circuit during the positive half cycle, obviously, and this current is also flows through the load resistance, but we already calculate the DC value. So what will be the AC value flowing through the load resistance? And this is I prime is equal to I minus IDC. This current is also flow through the load resistance, and we already calculate the DC value. So obviously this will be the AC value flowing through the load resistance. So what will be the RMS value of the AC component of the load current? So I RMS prime is equal to 1 by 2 pi 0 to 2 pi minus IDC তার হোল স্কোয়ার d omega t. Okay, and this is equal to 1 by 2 pi 0 to 2 pi square it I square minus 2i IDC plus ID square d omega t. Okay, and this is equal to 1 by 2 pi 0 to 2 pi I square d omega t. 1 by 2 pi 0 to 2 pi I square d omega t. See the expression, 1 by 2 pi 0 to 2 pi I square d omega t, and this is the RMS value. So this is I RMS square minus second part. See the second part here, IDC is constant, so the integration will be 1 by 2 pi 0 to 2 pi I d omega t, and this is average value 1 by 2 pi 0 to 2 pi I. So already IDC is here, and 1 due to the I 1 by 2 pi 0 to 2 pi I d omega t, so this will be 2i dc square plus here IDC square, average will constant, so 1 by 2 pi 0 to 2 pi d omega t give the 1, so this is equal to IDC square. Okay, and this is equal to, sorry, already consider the 1 by 2 pi, so 2 pi থাকবে না, so this is equal to I RMS square minus I DC square. This is the RMS value of the AC component of the load current. So what will be the value of the ripple factor? Ripple factor equal to I RMS prime by I DC, and we already calculate the value of I RMS prime, and this is equal to 1 by RMS square minus 1 by DC square by IDC, and this is equal to RMS square by DC square minus 1. And if you substitute the value of IRMS and IDC, we get I0 square by 4 by I0 square by pi square minus 1, and this is equal to pi square by 4 minus 1, and this is almost 1.1. So the ripple factor of the half wave rectifier, this is 1.1, and this is the ratio of the RMS value of the AC component of the load current to the average value of the load current. Thus the value of the AC term is greater for half wave rectifier. So the performance of half wave rectifier is not good. So we maximum case we use for rectification full wave rectifier, and I will discuss about full wave rectifier in the next class. Now I want to calculate efficiency of rectification. Efficiency of rectification is PDC by PN. Efficiency of rectification mean আমার কতটা AC signal transform into a DC into 100%, and PDC means power mean current into voltage, and from Ohm's law we know I into R, so power means I square R, and average DC power mean already we calculate that average current, so IDC square into RL. The loaded across our DC voltage develop করবে, and the AC current in the circuit is RMS current, and the total resistance in the circuit is forward bias resistance plus load resistance into 100%. Okay, so this is the efficiency of rectification, and if we substitute the value of RDC and IRM square, we get 4 by pi square into 1 plus RF by RL into 100%, and this is equal to 4 by 9, and this is almost 40%. Obviously if we consider RF is equal to 0. So the efficiency of rectification for half-wave rectifier is 40% maximum. This will be maximum if we consider the forward bias PN junction resistance is 0. এর আরও কম হতে পারে. So the efficiency of the rectifier, half-wave rectifier, is not good. So we prefer for rectification process always full-wave rectifiers. But in the next class, I will discuss about full-wave rectifier. Full-wave rectifier. Thank you.